And my goal, if I can, we'll see, is to try and get through as many of these things as we can. Now, some of them are definitely overlap, and some are overlap, and then I'm adding extra bits to it. So it's always good to see things again, right? It's not a bad thing to have a little bit of revision, you know, a rolling revision. So we're going to go through essentially 8 topics. That's my goal, at least. So let's start with mean and median. And we're going to do stuff that we know, and then I'm going to add something to number 1 that we might not have known. These are 2 numbers. We call them numerical summaries. The mean and the median, their job is to tell you the typical person, right? The typical person in the class, right? So if there was 100 people in a huge university class, which by the way you can get sometimes, and the mean was 21, you get an average of 21, right? Because you normally use the word average when you really mean the word mean. Both of these things are called averages, by the way. So that's a bit bad. The English language uses the word average when really they should use the word mean. So that's when you add them all up and divide by how many. And this one's the middle number in order. So I'll put a little definition between each of them. So this one is the middle number. Middle number when everything is in order. And this one is, this is one where you add them all up and you divide by how many. That's not very mathematical, but I'm just trying to convey what it is. Right? So let's suppose, just for argument's sake, that this professor said, going to give you a test, say 100. And as long as you get better than the average, I'm going to pass. I'm going to pass you. If you get less than the average, you're going to fail this class. And you might think, well, I've probably got a 50-50 chance, right? Average is about in the middle, right? Okay. Just as good a chance above or below. Well, not always. That's why this is a little bit different. So this is the test. And it was a stinker, yeah, test. And he's going to use the mean to decide it. So let's see what the class looked like. I'm going to keep the numbers pretty small. Somebody got 10 out of 100, somebody got 20, somebody got 20, somebody got 25, and guess what? James got 100. Okay. Let's see what the mean is. You add up all the scores. And you divide by how many numbers there were. So I should do it in my head: 20, 40, 150, 170, 175. So 175 divided by 5. And I got 35. So how many people are going to pass this class? I know there are only 5 in it, but how many are going to pass? Just one person. Why do you think, I hope you agree with me, I think that's unfair. That you just have to be better than average. And isn't it unfair because of this genius? Wasn't that test probably a really, really hard test? And there's one, have you ever got a class where everybody has a real hard time and one person's floating up? That was easy, right? Doesn't make you feel very good. But in this case, it's worse than that. Doesn't it mean you failed the class? So what was the problem? The problem was this number here. We have a special name for numbers like that. They're called outliers. Aren't outliers exceptionally big or small numbers, right? Extreme numbers. That's what an outlier is. Can outliers affect the value of a mean? As you see here, isn't that much bigger than most people in that class, right? I mean, 4 people didn't even get close to that. 10 off was the best. So here's one way of looking at how to go for an outlier. Now I'm going to show you a better way, hopefully at the end of today. If you take that off your list and you just look at the 4 people that were left and you calculate their mean, 40, 50, 75. Would you agree that that number is a fairer representation of what the typical person got in that class? Right? Would you agree this mean is a better, fairer way of doing it? So I'm doing a little 75. I'm going to divide it by 4. And the answer I get is 18.75. Right? Which is not bad. So what I'm trying to get across here is that outliers affect the mean in a disproportionate way. So if you are dealing with a set of data and you notice that there's an outlier in it, it's probably a good idea to remove that from the data set and work with the other numbers. Give you an analogy. Suppose we collected data on everybody who stays in Washington State and we figured out what your wealth was. So your wealth is, if you sold everything you owned, right, and you paid off your debt, some of you hopefully will have positive numbers, right? Can you imagine? I might, because I'm older, I'm worth 100,000, right? Brendan's a student, so he's worth $10, right? Whatever it is, right? You get what you get. If you did that with usual kind of numbers and you used the mean, you would get a reflection on the typical wealth of Washington State. But we have some really bad outliers in Washington State. Don't we have Bill Gates, for instance, and his wife? Can you imagine what 100 billion would do when you share it amongst all the people in Washington State? Doesn't it end up that if you use Bill Gates, for instance, and his wife's data, and a couple, does the Amazon guy live here? Let's say he lives here as well. Couldn't you end up with the average wealth of people in Washington is $1 million? Right? It's not $1 million, right? I mean, even old people who've got a house, hopefully have got a house, right? And they might be worth $500,000 or $600,000. Not many people get to that number. And that's caused by the outliers. So we don't like them. Outliers are bad for the mean. That's our story for today. Now, I'm going to take that same class and the professor said, yeah, you're going to pass if you have the median or better. Not the mean or better, but the median or better. Now, in this data set, there are only 5 numbers. Would you agree that guy there is the median? Did that outlier affect the value of that median? Does that isn't that a good number? Isn't 20 a good number? It's right in the middle of everybody's score. Do you see how medians are not affected by outliers in any significant way? In fact, if I took that outlier away, wouldn't the median still be 20? So that's good news. Medians don't care about Bill Gates. So if I found the median wealth of people in Washington State, that number would be pretty accurate for the typical wealth of a person in Washington State. Because isn't Bill Gates and his wife just one person? And isn't there, whatever it is, 7 million people in Washington State? Can you imagine he's not going to be anywhere near the middle? He's not going to distract the data. Are we cool with that? So that was a little bit different, just added something to what we've got. The next guy we're going to do is new page, I think, is going to be the 5-figure summary, interquartile range, and outliers. And I believe we've covered them, didn't we? You remember? Right, so these two are going to be pretty quick. So I'm just going, for completeness sake. So I've got some data. The minimum is 5. Q1 is 10. The median is 15. Q3 is 25. And the maximum is 90, right? Now, for that set of data, we have now got a 5-figure summary, right? Imagine we calculated we got it, right? We would like a guy called the interquartile range. He is a measure of how spread out it is. And you do it by doing Q3 take away Q1. So in this case, 25 take away 10, and you get the answer 15. And we've covered that. I would like to check, or test is a better word. Is that guy an outlier? Now, to do outliers, you calculate 2 other numbers. They're called the lower fence, and the other one is called the upper fence. And I know I'm putting you on the spot, but some of you have nice fresh brains. Can anybody remember the formula for the lower or the upper fence?
Q3 plus 1.5 times IQR.
Agreed. And what's the other one, the lower fence side?
Q1 minus 1.5 times the IQR.
Agree. You see, it's not perfect, but it hasn't got a kind of symmetry to it. It's not just random all over the place. And we've accepted that in the statistics world as a test for an outlier. So would you agree it's probably not worth testing 5? Would you agree I could do it, but I'm not going to. Would you agree it's safe? Would you agree? Can't see that being an. On the other hand, would you agree that there's a fighting chance at least, or a good chance, that 90 is going to be an outlier? Can you see the difference from here? Yeah. So I'm only going to do the upper fence. So Q3 is 25 plus 1.5 times 15. And that's going to be 25 plus, I guess I should do that in one go, but it's too late now. 1.5 times 15. So that's 22.5. And so we have 47.5. Now, if you're bigger than the upper fence, which you clearly are here, would you agree that guy is an outlier? And I can say that even although I don't know what the other numbers are, because the test just says if it's bigger than the upper fence, it's an outlier. End of story. Right? Isn't that better than, yeah, it looks like it, but I'm not sure. Some Abra thinks it is and Brendan thinks it's not, right? All that vagueness that we do when we look at the picture or we just look at the data. Isn't it just nice? We got a rule and stick to it and don't worry about it. If it says it's an outlier, okay, it's an outlier, move on, none to see here. Now, how about creating a box plot when you know you've got an outlier? So I'm going to have to change the data a little bit. That's 90 and that's an outlier. Can we pretend that the next number after that, right? The next number after 90, the next biggest number was 60, just for argument's sake, right? We're now going to look at what does a box plot look like when you want to tell people about the outlier, right? There are two ways you can show that. I'm going to show you both, because in some circumstances, one method is used, and in other circumstances, you use a different one. So the first method is we're going to indicate it up to 90. So I'm going to go 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay. And the first guy is 5, so that's about there. Then it's 10, so that goes there. Then it's 15, which is about here. Then it's 25, which is about here. And then you have 90. Oh, and you've got 60. So one way to indicate that you have an outlier is you draw your box plot, but see the end of your tail, don't stop at 90. Don't travel all the way to there. Stop at the next biggest number, that's there. And then just put a little dot, or sometimes a little asterisk. And that's how you would visually indicate that this guy is an outlier. Can you see that the rest of the data just kind of stays put? Right, it all goes where it is. Of course, to do that, don't you need to know the second biggest number? So we'll assume you've got all the data to do that. The second method is a little bit different, and it goes something like this: 0, 10, 20. You notice that my scale's bigger this time. In this case, you got a 5, you got a 10, you got a 15, you got a 25, and you got a 60. And then you write down 90 omitted as an outlier. So you just write down a little sentence. I'm not using 90, it is an outlier. And the reason why sometimes you put it in and sometimes you put it out depends on how bad the outlier is and how distorted your box plot becomes. Isabel, what's your question?
Oh, it's kind of an unrelated question, but I was just curious. If you're given a set of like 20 numbers, let's say, and you need to find like the Q1 or the Q3 in that data set, how do you do that?
There's a long way to do it that you're going to have to watch a video for, but I'm going to show you today the short way of doing it, which is using salt.
Okay, cool. I was just wondering if you were going to know about that.
Yeah, because if you look at some of the homework questions, you're probably going to say, oh God, I don't want to have to do that by hand. Because it does take a long time if you do it by hand, because you have to put them in order. Then you split the middle to get Q2, then the lower numbers you split it, and the upper numbers you split it. And it's doable, but it's long. So you might think, if I can return it up, why do you do it sometimes and why do you omit it? Can you imagine a different data set that looked like this? Can you see how distorted the data became because the outlier, the Bill Gates, was so big and the rest of the numbers were kind of crunched to nowhere? In a world like that, wouldn't it be better to just omit the thing, draw a nice blown up version of that guy, and then just say, you know, Bill Gates, whatever his number is the outlier? So in a practical, this is how you would do it in real life. In practice, if you're doing a summary diagram using a 5-figure summary, watch out for outliers. You may want to remove them from the entire picture and draw the box plot without it. In other cases, it's an outlier, but all you need to do is indicate it, you know, by putting it in the diagram, but as a little asterisk or star. Isabel, you got your hand up again or just forgot to take it down?
Oh, my bad. I forgot to take it down.
I think because it came to me and she's got her hand up, or did have her hand up, that I'm going to tell you a joke about a really bad student who didn't pay attention. Not that Isabel is a bad student, she's a really good student, by the way. But this student didn't turn up to class, didn't study, didn't do anything. And he turns up for the day of the exam. And when he turns up late, of course, goes to pick up his test, and it's his lucky day. It's 10 multiple choice questions, and the answers are just true or false. And he sits down right in front of the professor, and he reads the first question. He has his coin, and he flips it up, and he goes like that. And he reads the next question, flips it up, goes like that. So the professor's watching this and thinking, well, I know what he's doing, right? He's guessing, right? That's what he's doing. And so when he got to the last question, he thought he would just get his test paper back, but he didn't. Once they finished the last question, the student turned it over and went back to question 1 and went to question 2. And so he goes over and says, what are you doing? He says, I'm checking my answers. Abra, I got this shaking head thing. Isabel, did you like that joke?
Yes, I did.
Was that bad, Brendan, that it was good? Brianna,
I like that joke.
You got an opinion on that joke, Brianna?
It was good. I shook my head at first, but then I laughed.
Okay.
Yeah, not gonna lie, that one took me a second.
Abra has not changed her mind yet, which she's totally entitled to.
It was a good joke. I just was like, why would that's stupid that he did that?
Okay, I'll give you that one. If you go into teaching, you will not be amazed by how stupid professors and students can be. And that includes me. Okay, where was I? Oh, our list of things to cover. I promised you salt, didn't I? Someone went and I said, how can we do it if we don't want to do it by hand? Well, sometimes you get really lucky, right? And you can use a feature in WebAssign called SALT, Statistical Analysis or something it stands for, I'm guessing. I know S is statistics, that much I can tell you. So let's show you a question. Here is a big set of data. There are 20 numbers there. Now, I know how to do minimum and I know how to do maximum, but would you agree that trying to do the rest by hand would be boring and take too long? Wouldn't it be nice if we could do it using SALT? Great. So you hit the SALT button and this guy appears. And then, well, maybe you can tell me. I'll tell in a second if nobody comes up with it. Which one of these headings do you think I'm going to find the 5-figure summary? If you were a gambling person, which of those headings do you think the 5-figure summary is going to live?
Maybe charts and graphs, or
that's where the box plot's going to live. So you're close.
Page said descriptive statistics.
Yes, that one. Now I just clicked on it there. Now, do you see that there's a whole load of numbers here? Right, there we go. The 5-figure summary is these 5 numbers at the end. Do you see it's as quick as that? Max, min, Q1, median, you know, the whole set. Do you see they're all there? Isn't that kind of helpful? Makes life a lot quicker. Right, now I'm going to move that window and just go here and use their values. Well, I will once I get, oh, darn it, there's a window in the way. Right, gotcha. Okay. Oh, that's weird. Minimum is 158. And Q1 is 178. And the median ends up being 195. And Q3 ends up being 203. And last but not least, the maximum value is 240. Now, wasn't that very quick? Can you imagine doing your homework, you hit the sort button, you just go to the end and you write the 5 numbers down, right? And you're done. You lot are not as impressed as I am that that software does this, but it does. Isabel, yes.
So did you, I must have missed it because I was looking at something, but did you input all those numbers up there into the SALT program first, and then it gave you those numbers?
When you hit the use SALT button, it does all the uploading for you. You don't even need to
Oh,
tell
okay.
it. It's so automatic, it's not true. Now,
That's cool.
it is cool. I think so. Now, do you see there's 4 box plots here? If you've got this guy, shouldn't you be able to figure out which one of these 4 is the right one and then just pick it, right? It does have a feature, I'll show you on this one, but I don't like it. If you hit charts and graphs, do you see there's a guy there called box plot? Why don't I like it? Well, if you look at it, do you see it's pointing the wrong way? It's vertical instead of horizontal. Secondly, do you know you have to turn your head to the right, not to the left? And if you do it the wrong way, you might pick the wrong answer because you want the small numbers to be on the left-hand side, right, when you turn it around. It's not worth it. I've decided it's not worth it. I think a bit of paper, couldn't you sketch that yourself and figure out who the right one is? Now, there may be, whoops, the wrong question. Where is it? If I lost it. I've gone and lost it.
It was number 6.
Thank you. There, I scrolled too back. Right. One of these 4 is going to be the right answer. Let's do a little test. Because in this case here, none of these 4 pictures had an outlier. Agreed? So obviously there can't be one, but let's pretend they asked us, is there an outlier? And let's check 240. Okay. I'm going to write down what I need to know to check 240. So I need to know Q1. So I'm writing that down. It's 178. I need to know Q3, which is 203. And I'm going to test if 240 is an outlier. So far, so good. Right. Let's go in and do the thing. Okay. Since this is a big number, don't I only need the upper fence? So the upper fence is going to be Q3 plus 1.5 interquartile ranges. And I just realized I forgot to calculate the interquartile range, so I'll do it now. It's 203, that's Q3. Take away 178, so that's 25. So the upper fence is 203 plus 1.5 times 25. So on my calculator here, 203 plus 1.5 times 25, and I get 200. Whoa, would you look at that? 240.5. Didn't it just sneak in by the skin of its teeth? Isn't 240 totally safe? If it had been, I don't know, 241, wouldn't it have now been an outlier? So as long as you are the upper fence or lower, you're safe, right? You have to be, even if it's a tiny bit, 240.6 or whatever, now you're an outlier, right? So we'll give you the benefit of the doubt, because I can you imagine a story where this is 250 and that's 250 and you're thinking, oh, what did we do? 250 makes it, right? You're still safe. You have to be bigger than the upper fence. We cool with that? I'm not going to test the other one because I'm 100% sure it's not an outlier, but you could test it, couldn't you, if you wanted to? Are we good? Any questions before I move on to the next one on my list? Eric, you're quiet today. Is that a good sign? Okay, let's do this guy. And mean and standard deviation. We already know how to do mean. let's move on and talk. Oh, new page, I think would be nice. Mean. Okay. Where shall we go this? The mean is a number, right? It's a measure of the typical data point. So the mean is like if you had a class of 50 students, the mean would be like the average age of them, right? Standard deviation is a guy you haven't met, so he's new. It does the same job the interquartile range does. You know, the interquartile range kind of gives you an idea of how you spread out the data. So does the standard deviation. The calculation of the standard deviation is ridiculously ugly. You do not want to even try and do it by hand. If you feel like you want to see more about it, then feel free to look it up. This is what it looks like. If you want to see it in sigma notation. Right. Do you really want to do that? Well, first you got to figure out what all that notation means, and then you got to do it. Trust me, you won't even want. See, even 5 numbers, I'm not exaggerating. Just to find the standard deviation of a data set that only has 5 numbers would easily take you over 20 minutes. So will we just say, thank you, Salt, because you're going to tell me the answer and we'll live with that, right? Okay, so all you'll get is you hit the Salt button and I'll go and I'll show you a question that does that in a few seconds. That does that. So this is a measure of the typical person. And this is a measure of how spread out it is. I'll give you an example. Suppose I had 2 statistics classes, class A and class B, and their mean age. Oh, by the way, mean, we very often use that symbol. It's called X bar. That's how you read it out loud. X bar. Let's suppose of the first class, the mean is 25. And the standard deviation, SD for short, is 10. And in the second class, the mean is also 25, but the standard deviation is 20. Now, that's the only 2 numbers I'm telling you about my 2 statistics classes. Isn't the average age about the same? 25. But isn't this second number, the standard deviation, isn't this one a lot bigger than that one? It's technically twice as big. If you were thinking about the classes, what's this telling us about the 2 classes? Are they identical or are they different in some way?
They're different.
Right.
Class A, the ages are more closely grouped together.
Yeah. And in class B, aren't they all over the place? Can't you have an average of 25 made up of everybody 24, 5, and 6, right? And couldn't you have another class where the average is 25, but the age from 15 to 50? Aren't they both still got the same average, right? The same middle person, whatever you want to call it, but one is much more spread out than the other. So that's kind of what the measurement for standard deviation does. And it's got an extra little benefit. We can use it to test for outliers. And this is the test for outliers using standard deviations. We don't have upper or lower fences, right? And we don't even actually, as far as I know, we don't even have a name for them, although they're almost like the same. But for want of a better word, typical data is inside the interval X bar plus or minus 3 standard deviations. So X bar in this case is 25 plus or minus 3 standard deviations. So for this class here, it'd be 3 times 20. And that probably wouldn't make much sense in the big scheme of things, but we'll still use it. The mean, take away 3 standard deviations, and the mean, add 3 standard deviations. At one end, I can do that. Can you see you can add that? Now, sometimes you have to tweak your interval to take account of context. The context here is people's ages, right? Would you agree that 25 take away 60 is some kind of negative number, right? And I'm going to go in the A side of safety. I guess somebody could have brought their newborn baby into the class and I counted them, right? So would you agree 0 to 85 is the typical range? Can you see that that class has got a lot of all sorts of ages in it? And some kids probably, or whatever, who knows? So if you're going to be an outlier, don't you have to be bigger than 85? Right, so an 86-year-old would be the only outlier in that class, or a 90-year-old would be an outlier. Let's try the other one. Let's look at this one. So it's the mean plus or minus 3 standard deviations. The mean in this case is 25 plus or minus 3 lots of 10. That's 25 plus or minus 30. On this side, it's 55, and the other side, we're going to call them babies again. Wouldn't a 60-year-old be an outlier in this other class? If you were a 60-year-old in this class, wouldn't you be an outlier? If you're a 60-year-old, would you be an outlier in this class? No. If you're a 70-year-old, you're an outlier. If you're a 70-year-old, you're not an outlier. Isabel.
So when you do plus or minus, if it comes out as a negative number, do you just do 0?
On context, yes. Since this is age, can we pretend a different context? This was temperatures, right? You know, over a year, right? If it was temperatures, I would allow negative numbers because you can get negative 20 degrees, can't you? At least in some parts of the world.
Okay, so it depends on like what you're measuring then.
Yeah, pretty much.
Cool.
So if you're measuring age, weight, height.
Yeah. Will the numbers or will the questions say that like on a test?
Yeah.
Will it say it's okay to go negative or something?
Well, I wouldn't say it's okay to go negative, but it would say the age of 20 students, and you'd say, okay, age.
Okay, yeah, no.
Is the end of the story.
Okay.
So that's what I mean.
Use common sense.
Right. Yeah, use common sense. So if it says the temperatures in, you know, a town in Nebraska over the last year, and, you know, in that case, negatives would be fine, wouldn't they? Because temperatures can be negative. Is that cool now that we have rules for testing for outliers? We don't need, I seem to have lost a lot of people. What's going on? Let me stop this for a second. No, that's weird. My windows were closed, sorry. I only thought there were 5 people in the class, but I can see you now, or at least the ones who've got the thing. Okay, I lost the place. What was I talking about there? I was talking about outliers and intervals. That much I remember, but what else was I saying?
Talking about like how you test for outliers.
Right.
Right.
And context decides if 0 or not. That's pretty much it. And the fact that isn't it good that we now have an unbiased test, a number test. So if I said to you, Abra, 72-year-old in this class, right, the second class, you could say not an outlier. And Brendan would agree with you, and Eric would agree with you, because we've now got this universally accepted test. If you're bigger than, mean plus or minus 3 standard deviations, right? If you're outside that interval, you're an outlier. Okay. Now, how can we use that idea of an outlier in, say, a medical context? Now, I'm going to make this up because I'm not a medical person, but you could probably work on this and come up with a realistic one. Let's suppose that there is a test that they're doing and it's your potassium level, right? If you're a doctor, wouldn't you like to know whether, a range of normal typical values is, and when somebody's got an abnormally high potassium level, because couldn't that be an indication of some kind of disease, or an abnormally low potassium level? So what they do in these kind of things, have you ever been to a doctor? Well, I get it all the time. I get blood tests forever, right? Because of all sorts of issues I have, right? But you get a blood test and doesn't it tell you this is the normal range and you're low or high or something, right? You might wonder where that comes from. So this is my pretend one of what they do. They have collected tons of data on the population, right? And one of those things is probably thousands upon thousands of blood tests of potassium level. And they end up with, this is the bit I'm guessing, that the mean level for potassium is 30 units or whatever it is, right? And that the standard deviation for potassium is 5, right? Just for argument's sake. So what would be considered extremely high potassium level or extremely low, right? So I'm going to down here, going to do a little number line when we find it. So first thing I'm going to do is mean plus or minus 3 times the standard deviation, right? My little window guy. And the mean is 30, and it's plus or minus 3 times 5. So it's 30, add or subtract 15. So on the small side, it's 15, and on the big side, it's 45. So I'm putting a little scale here. 0, 5, 10, there's 15, 20, 25, 30, 35, 40, 45, 45, and so on, right? 15 is about here, right? And 45 is about here. Can you see that people with potassium levels where my finger is pointing, aren't they outliers? Extremely unusual high values, right? So wouldn't we say that these were high potassium levels? We might even put in the word extremely. Do you see how the medical profession can now put bans on what's normal and what's not normal for any level? Blood pressure, potassium, cesium, whatever you want, right? What would we call these people whose potassium levels are like 5, 10, 7, that kind of number? What would these people be?
Abnormally low potassium.
Yeah. Okay, Isabel, what you got?
It kind of reminds me of like a box plot with the Q1 and the Q3. Is that kind of what those two values are that the standard or that we're kind of calculating?
They're kind of like those. Yes, you're right. They're kind of, we don't draw box plots for this type of data, but they do a very similar kind of job. Isn't it kind of signposts on the way to the end? So these are like the Q1. They're not exactly there, but they're in that kind of.
Okay, I was just wondering if they were the same thing or not.
Not the same thing, no, but they kind of share a kind of visual similarity, but not the same thing. Now, have you ever noticed that sometimes they don't just tell you you're really in trouble? Sometimes they say it's high, not extremely high, but just high. So can you imagine how that might work? This is not typical, but couldn't you do plus or minus 2 standard deviations? Now, if I did plus or minus 2 standard deviations, I would get here. So people in this range have got a high potassium level, and people here have a low potassium. And these people in the middle, that would be the normal range. Isn't that quite a powerful way to use these summary statistics? So that when you get a whole blood test, your doctor's going to say, your potassium is really low. I don't know what makes your potassium go low, but maybe it's your thyroid's not working right or something. And they can look at this and they can, with I'm sure lots of other tests, put them together and maybe come up with a possible reason for it. Maybe it's a diet reason, that's an easy fix, but maybe it's something more serious. Any of you have kids or have had kids, right? Eric, when your kid was growing up, when you took your baby in for, I don't know, I'll call it the 6-month checkup, you know how you take your baby to get a look about, or is it 6-month-old or whatever? Don't they do things like measure its weight and its length, right? And don't they then say, your kid is bang in the middle where it should be for a 6-month-old baby? Or, hey, you got a really tall kid here, right? Or, yeah, your kid's a little bit in the small side, right? And how do they know that? They do it because they do this. Can you see that you've got tons of data on 6-month-old babies? So can't you find the mean and standard deviation and build one of these tables? And that stops doctors just using, well, I've seen a lot of babies in my life, and for a 6-month, that kind of baby looks a bit skinny to me or a bit tall to me. That's kind of vague, isn't it? They now just look up tables. I bet you could go online and do that if you wanted to, couldn't you? Find what's the typical weight of a 6-month boy, different from a 6-month girl, correct? So they have tables for boys and girls. And some blood chemistry is also different. Don't women and men have, if in some places, don't the normal levels are different because females and males have different body chemistry. A little side issue, but I want to kind of show you that this stuff is helpful, right? For different people in different places. This is good stuff. So I'm now going to show you, oops, check that off my little list, I'll do blue. Symmetric and distributions. We've met this guy before. Can you remember a symmetric distribution looks something like this? Right, nice symmetrical, not perfect, nothing's perfect, but it's, so maybe make it a bit longer, right there. We call that bell-shaped or symmetric. So this is bell-shaped data or symmetric. If your data has that shape to it, you are now allowed to use this. I believe it's called the empirical rule. And it is an amazing property that you probably would never have guessed, but it's been shown to work, so we like it. Suppose we take the IQ test of a lot of people, and the IQ has a mean of 100. Would it surprise you to, I don't think it should, would you surprise you to find that the middle of the hill, the tallest, is IQs of 100, right? So the mean tends to be right in the middle where the hill gets to the highest. Now let's suppose that we had a standard deviation and it was 10. So if I do 1 standard deviation, I get 110. I do 2, I get 120. I do 3, I get 130. And then if I go back the way 1 standard deviation, I get 90. Then I get 80. And then I get 70. What the empirical rule says is that if you take the mean and you add and subtract 1 standard deviation, you get 68% of all the people in your sample is in that range. So in my IQ of 100, plus or minus 1 standard deviation of 10. So what would that be? That would be anybody whose IQ is from 90 to 110. 68% of the population, adult population of America, has an IQ in the range 90 to 110. And that's not just to do with IQs. As long as your data is roughly that shape, whatever the mean and the standard deviation is, can't you make one of these tables? Start at the mean and go, add 1 standard deviation, add 2, add 3, take away 1, take away 2, take away 3. And so that middle chunk from there to there, right? All of this chunk in here, 68% of all the people will have an IQ. All the data is in that range. Now, if you take the standard deviation and you add, the mean, and you add 2 standard deviations, you get 100 plus or minus what, 2 times 10, which is 20. So that ends up being the range 80 to 120. And in that range, 95% of the data is. So if you imagine me oops, I better go a different color now. Starting at 80 and finishing at 120, right? All this stuff, I think I'll put it here now. From here to here, 95% of all Americans have an IQ that is in that range of 80 to 120. Now, all I know is that it's symmetric in shape and these 2 guys. Yet, only with that information, don't I now know an awful lot about everybody? Now, you take it to the last one, and the last one is the mean plus or minus 3 standard deviations. So that's 100 plus or minus 3 lots of 10, and that is 70 all the way up to 130. And in that range, 99.7% of all the data lies. So if you took someone in the range of an IQ to 70, all the way up to people who have an IQ of 130, from there to there, in that range, 99.7% of the population lies. Can you see why they picked 3 to be an outlier? Isn't it very rare to be an outlier? Don't you have to be really, really way out there in the big, or really, really way out there in the slum? That makes sense. That's why they picked 3. Pretty rare event. Do you know what you call people in that area there? What would you probably call them? People whose IQ is greater than, say, 130.
A genius.
Yeah, that's probably where the geniuses are. Unfortunately, some people at the other end have problems. Mostly football players. Yeah, hitting their head too many times. Oh, Isabel thought that was funny. Good. Did you get that one about the football player, Eric? Okay, just making sure you're following my bad sense of humor. I hope nobody here is a football player. I could be in trouble. This is called the empirical rule, but it has another name, and I'm not making this up. I make lots of things up, but I'm not making this up. What I've just written down here is called the 68, 95, 99.7 rule. I'm not lying, that's its name. I actually like that name, because doesn't that name pretty much tell you the numbers you need to remember? It's not very flows off the tongue name, but nonetheless, it does its job. Is there anything about this that you would like me to talk a little bit more about? Isabel, what you got?
So is it always 1 deviation is a 68%, 2 standard deviations is 95, and then 3 standard deviations is 99.7? Is that always how it works? Is that the rule? Okay, cool.
That's it. Yeah, worth checking, double checking. Right. There's my name, right? We've already covered the outlier one. we're going to get to the next bit, but I want to make sure I didn't miss anybody in the previous one. No, we didn't. Good. So let me open this one up. We're now on to chapter 3. We finished chapter 2. So, hold that thought. We're going to calculate those horrible standard deviations that you are never going to do by hand, right? Unless you've got a death wish, right? You're going to let calculator do it, in my case, the TI-84, or you're going to use SOLE. In some of the homework questions, you don't have the salt button handy. And it's only in the questions where the salt button isn't handy that you're going to use the TI-84, and that doesn't look much like a TI, but it is meant to say TI. So I'm going to go to a salt button question if I can find one that's got standard deviation on it. I can never find things when I want them. Okay, where the heck are you? Okay, got one. Oh, no, darn. No. Would you believe it? I can't find a salt button, but I can show you the TI-84 one. So here goes. On this calculator, we are going to use it to find standard deviations of quite small data sets. So I'm going to pick question 1, and the numbers are 23, in my case, 24, 25, 26, and 27, because they have no imagination and it's nice small numbers, and that's fine. So first thing you're going to do is going to hit start button, and then you're going to choose edit. And you might end up with a whole load of data. So just keep hitting delete till it's gone, right? So it's empty. Now you type in your numbers: 23, 24, 25, 26, 27. That wasn't too bad. Right. Next thing you're going to do is hit start button again. Move over to calc and go to number 1 variable stats. Can you remember that's the exact same thing you did when you wanted to find Q1 in median using the calculator, right? So it's really just repeat the process. Now, when I hit this, I'm going to put in blue button 1. That's where the data is, and then hit enter. Now, on this page here, you've got all the numbers you want. Can you see that the mean is 25? Now, the guy that you're looking for is either this one with SX or this one with a funny Greek letter called sigma. Right now, you're only going to be interested in this guy. So to 2 decimal places, can you see the standard deviation is 1.58? I was looking, and for some reason I can't find one. Maybe I just missed it. But if you were doing the salt button ones, you could get that data, right? In fact, I've now figured out where to find it on the salt buttons, right? I'm going back to, I'm saying chapter 3, that's end chapter 2, I should say. I'm going back to numerical summaries for a second. Okay, and now I'm going to show you how to get standard deviation for a set of data. Right. Imagine this set of data and you wanted to get the standard deviation. Even using a calculator, would you agree that's pretty onerous and you probably had one of your numbers that you're going to make a mistake, right? So hit salt button. Go to descriptive statistics, and there it is. Easy to get. Now, on a calculator, it's not so easy, but you know, we'll live with what we've got. You want to see another one of these done on the TI-84? Okay, so let's pick some data from you lot. So what shall I choose? I want nice round numbers. How many times you've been to a restaurant, you know, like Red Robin, to sit down and eat, right? So that shouldn't be a very big number. How many times you've done that in September? Okay. So anybody who wants to volunteer that number, I'm putting mine in 3. Doesn't need to be Red Robin, it can be anywhere.
5.
5.
2.
2.
0.
0. 0 is a good number, it's allowed.
7.
One more.
Somebody put in the comments 4.
I will use it. Thank you. So can you imagine we collected, you know, 25 of you, whatever. This is our raw data. And we're going to use this raw data to find the mean and the standard deviation. We're going to use our calculator. And then I'll see what else I can come up with. So I'm going to go second, quit. Try again, second, quit. Go away. There we go. Second, quit. Why are you not quitting? I've broke my calculator. There we go. I cleared it. So I'm going to put this data into the calculator. So I'm going to hit Start. Number 1 is Edit. And just keep hitting Delete until the old data is gone. And then 3, enter 5, enter 2, enter 0, enter 7, enter 4. Right, that was pretty quick. And then the rest is kind of repeat yourself every time. So hit Start, move over to Calc, Choice 1, blue button 1. And the mean is about 3.5 times, and the standard deviation is about 2.4. I think he might be an outlier. Don't know why a number could be a he, it could be a she as an outlier, right? Numbers are non-sexist. So if I was checking for an outlier, wouldn't I just be looking, in this case, at the 3 standard deviations, because I think that's a big outlier, right? And so it's going to be, excuse me, 3.5. Excuse me.
Gesundheit.
Oh, thank you. 3 times 2.4. So that's 3.5 odd 7.2. And the answer we get is 10.7. I know you can not get decimal amount of meals, but we just live with that. Isn't 7 actually not that unusual, at least based on this very small data set? And we'll make the assumption that the data was normally distributed. I wouldn't be surprised. Bit big, but non-special. Now, if somebody had said 14, wouldn't there have been an outlier? Agreed? I don't think, based on the size of the mean, that any of these small numbers are going to be outliers, so I'm not going to bother testing them because I don't think you'd get that along. Are we comfortable that if I give you a small set of data that you can get the standard deviation using your TI-84? Right? And hopefully you'll find one. I'm sure there's one floating around. I just can't find it right now. If you got a salt button, isn't it even easier? Right, so that's how you're going to do standard deviation, no other way. So let's show you some special cases. I know the standard deviation for this weird data set. If standard deviation measures how spread out things are, what do you think the standard deviation number would be for that guy?
1.
That's pretty small. Any other suggestions? No, 1's good number. It's not the one I want, but it's good number.
0.
Yeah. Would you agree that 0 means there isn't any spread? And if all the numbers are 17, doesn't that kind of make sense? Now, what about this? These are two different sets of data, 1, 3, 5, 7, 9, and 4, 6, 8, 10, and 12. Now, I definitely know that their means are going to be different. Would you agree the mean of the second data is going to be bigger than the first, right? But although I haven't calculated the standard deviation, do you know I can tell you something about them? They're both going to be the same number. Standard deviation does not care how big the numbers are or how small the numbers are. Standard deviation only measures how spread out they are. Would you agree that these two data sets are spread out roughly the same way, aren't they? Now, I don't know what the number is. It's 0.3, right? Wouldn't both of them have a standard deviation of 0.3 in that case? So these are just some of the basic properties that you can use on standard deviations. That's not right. Are we good? Right. Let's look at some homework questions, and then I'll definitely come back to this page, I'm sure. Should check the chat. Anybody got? Interesting comments, but not necessarily ones I need to share. Where the heck am I? Oh, here we go. Okay. I hope you're looking at bell-shaped data, which I call chapter 3, but it's still chapter 2. Here is some data, calculate the mean and standard deviation. Can you see that in this data set, you would do the TI-84? I wish there was a salt button, but it is what it is. Now, question 2 says that the average number of hours a college student sleeps is 6.9, and that the standard deviation is 1.5. Now, do you see it's that 68, 95, 99.7 thing I was talking about? So, if you take this number, the mean, and you add and subtract one of these standard deviations, you get 6.9. Let's put this out somewhere. You get a 6.9 take away 1.5, and that ends up being a 5.4. You only would type in the number 5.4 here, right? And then you could have 6.9 add a single standard deviation, and that would come out at 8.27, yeah, 8.4. So now I can rub away out the calculations. That's the mean, take away one standard deviation. And this number here is the mean add one standard deviation. That means about 68% of college students get somewhere between 5 and a bit and 8 and a bit hours. Now, you're a college student. Is that roughly what you typically get, somewhere in that range? 68% of the people watching, that's probably true. Now, if you do 2 standard deviations either side, right? 2 standard deviations, I'll just do the first calculation. That would be 6.9. Take away 2 lots of 1.5, which is 3 hours, and that ends up being 3.9. And then if you go the other side, it's 9.9. So 95% of college students survive on 3.9 to 9.9 hours, allegedly. Don't know how accurate this data is. I don't know how you can survive on 4 hours of sleep. But I do know it's true. Do you know that there are some, off the top of my head, Winston Churchill, if you know about Winston Churchill, right? Second World War, British Prime Minister, all that stuff, right? He allegedly only slept for about 3 hours a night. He took what was called power naps, right? He used to take lots of little 10-minute naps all over the place. But physically, you know, going to bed, getting up, 3 hours, that's what he did. So I guess for some people that might be true, right? 9.9, I think that sounds like a teenager to me. Well, at least a teenager in the weekends. And I'm not doing the last one, but can you imagine 3 standard deviations in 99.7? So do you see that's the question to do with the 6 to 8, 95, 99.7? That's what they look like. And there's your range. Can you see here's another one to do with people's heartbeats? And can you imagine 4-year-olds? Wow, 4-year-olds' hearts beat a lot faster than mine. Anybody in the medical world, is that true that kiddies' heartbeats are a lot faster than adults? Yes, it is. Nobody says it's not. TI-84, do what you need to do. Okay, we are finished that question. We are rocking and rolling here. So this is going to be my last topic for today, but it'll take a while. Z-scores. Their full title, that's typically not used, is Standardized Z-scores. And this it is. Americans are really nice to me. See, if I misspell something, they don't think I've misspelled it. They just think that's how you spell it in Britain. But standardized Z-scores. Most of the time, I just misspell it. What these are used for? These are ways in which you can compare 2 scores. So this is basically how to fairly compare 2 scores of 2 sets of data, or 2, whatever you want to call it. So let's have 2 classes, Class A and Class B. And Class A is an English professor at university. And this guy, and you might meet professors like this, you can meet them. His attitude is, nothing is perfect. No essay is perfect. So he never gives 100%. In fact, he's a pretty rough professor. And he gave an exam. And by rough, I mean he gave hard tests to do. And the average that these students got was 50. And the standard deviation in this class was 15. And then there was class B. And class B had an English professor. But this is one of the huggy English professors, right? Which now gives me a chance to tell one of my bad jokes. If you ask a mathematician, what's 1 + 1, right? If you ask a math professor, what is 1 + 1? The answer will be 2. Always is 2, always will be 2. If you ask an English professor, what's 1 + 1? Do you know what their answer is? Well, does it really matter? And can't we all be friends anyway? Oh, come on, that's a good dig at English professors. Okay. Abra, is that you agreeing with that statement or not?
Yeah, I'll agree with that.
Is that your experience of English professors or some English professors?
Yes.
Now, this English professor gave an average of 70 and a standard deviation of 10. So there, in my story, there were twin girls, right? Mary and Jessica, right? Mary got this professor. And Mary, she got 75. And Jessica, I think I called her Jessica, she got 80. And when they got home, they were arguing to their mother who did better in their English. And Jessica went and said, I got 80, Mary only got 75. Hey, I obviously done better. Do you think that's a fair representation of reality here? Just because you got a bigger score, does that mean you did better?
No,
Because
not at
remember,
all.
no, couldn't this be a dead easy test that even I could probably get 80 in? And couldn't this be a really hard test and I'd be lucky if I got 60 in it? Because these are not the same test. If these were the same test, you know, a standardized test, yeah, I'd go for it, right? If everybody's doing the same questions, yeah, 80 is better than 75. But that's not the story here, right? Really hard test, pretty easy test. So the question is, how can you fairly compare them? Well, what you do is you calculate a guy called the Z-score. So this is going to be the Z-score for Mary. And over here, this is going to be the Z-score for Jessica, right? Now, since I've already said I don't think that that's a fair comparison, who is your gut feeling for who actually did better under the circumstances? Which one of those? Mary. Would you agree it's harder to get 75 in Mary's class than it is to get 80 in Jessica's class? But we can't just do impressions, right? We need to have a way of proving it, right? And so here's the formula for the Z-score. It's the data, right? Whatever you got in the test, take away the mean, divided by the standard deviation. And then what these standardized Z-scores are doing is that they are taking into account not just the mean, but how spread out the data is, because you agree that's part of the puzzle, right? Of how hard it is to get something, right? So if we take Mary, right? She got 75. The mean in that class was 50. And then you're going to divide it by 15. And then you do that in your class and, oh, I'm going to show you something that you can easily screw up here because I was about to do it. Do not do this calculation. This is the wrong version of that calculation. Oh yeah, 75, take away 50, divided by 15. Does that look right to you? Because it's not right. You'll get an answer of some ridiculous number. You need a bracket. If you're going to do this in one go, you need a bracket. And the Z-score is about 1.67 if you round it off. Why do you need a bracket around that calculation? Why is the 1.67 right and the 71 bit wrong?
Because you need to put the brackets need to be around it because you have to do that part first before you
Right.
divide the 15.
Ordinary calculation, exactly. Ordinary calculation. Now, what is going to happen here is that we're going to get a Z-score for both. And the person who gets the biggest Z-score was the harder of the two to get. And therefore, they're the ones that did best. So if this works right, shouldn't that 1.67 be better than this one? Meaning bigger. So let's see what the data says. She got 80, which is good. Take away 70, divided by 10. And I can do that one in my head. You see how that works? Now, this is actually used, this technique of standardized Z-scores is used in a lot of situations, and you don't even know that they're being used. Have you ever heard of things like grading on a curve? And you think, what's the curve they're talking about and how's it affecting the grading? Very often they're using Z-scores there, right? In a lot of universities, at least a lot I've heard of, it's not universal, but there's enough there to make it. They don't like the fact that students will take a professor that gives easier exams, and they will avoid the professor who gives more difficult exams, provided that everything else remains the same, because some people are really good at being professors and some are really bad, right? And so what they do is, it doesn't matter who you get, you all get a standardized Z-score, and then they give out the grades based on that. And it could be something simple. Can you imagine, well, here's something I haven't told you, but it's true. Do you know that when you calculate Z-scores for people, Z-scores, no matter where the story is, pretty much always end up in the range 3 to -3. Any idea why that's the case? Why is it 3? Because we've kind of touched on a 3 that happened earlier today.
Because of the standardized deviations and calculating outliers?
Yes, 3 standard deviations. Do you know the Z-score is how many standard deviations you are away from the mean? So they typically, so what would a university do? They might do something like, if you got a Z-score between 2 to 3, I'll give you an A. If you get a 1 to 2, I'll give you a B. If you get a 0 to 1, I'll give you a C. If you get a -1 to 0, I'll give you a D. And if you get less than -1, you failed the class. Can you see that's a much fairer way of distributing grades? So it doesn't matter if you got a really hard, exam with a really stringent professor, or you got a really easy one. Won't the Z-scores balance things out fairly? Because if you get really easy professor, don't you have to get 95, 100% to get an A? You need to do really good. Whereas, Mary only needed to get, well, what was she getting? She'd get a B, right? Pretty good. I think that's a really cool place to start. Did we learn some cool stuff today?
Indeed, we did.
Aidan knows the right answer. Okay, guys, say hi and bye-bye, and I will see you all on Wednesday.
Bye. Thank you.
You're
Thank
welcome.
you. Bye.
Right, I'll hang about